boundaries in which this electron can exist. The closest being n equals 1, n equals, I think we go up to 5, 6, whatever. Point being, the farther out that that electron is located, we said the more energy that it will have. Okay? I use the analogy of swinging like a ball around on a piece of string. The longer that string, the more energy and momentum that ball can carry. Now, if that were true, what do you know about, think about light, what we just talked about with wavelengths of light. What color of light has the most energy, the blue end or the red end of the spectrum? Which has the most energy? The blue end of the spectrum, because it has the shortest wavelength, right? Shortest wavelength, higher frequency, higher energy. Okay, so that's what you can see that's indicated by these arrows here. I want to show you that if this is a hydrogen atom, and at its normal state, we'll say it's traveling here at the n equals 1 region. Okay? If it absorbs energy, whether it's light energy, whether it's electricity, some sort of energy is input into these atoms, what can happen is that electron, remember hydrogen only has this one electron, right? This one electron could bounce up. Why would it bounce up? Because it absorbs more energy. And one of the fundamental laws of the universe says that energy cannot be created or destroyed. We just have to deal with it. We have to move and shift things to compensate for energy changes. So if it absorbs energy, it cannot stay here. What it will do is kick itself up to the least amount of times that it can go, depending on how much it's absorbed. And as soon as it gets to a point where it can handle, it moves out to a distance away that it can handle that energy. That's what it's going to do. Now, when it does that, you need to understand that this hydrogen atom is very unstable. It does not like to be this way. So almost instantly, as soon as that happens, that electron falls back down. So it falls out, and then immediately it falls back down. So notice what happens. It's basically like a transfer unit. Energy comes in, it gets messed with inside the hydrogen, and the hydrogen lets it back out again. Very, very quickly, almost instantaneously. Now, when this electron bounces back up in order to absorb that incoming energy, notice that this is a lot of energy that's coming in. With high energy situations, we use blue to symbolize, because like with light, blue light has higher energy. So this is coming in at a higher energy, and now what ends up happening is the hydrogen does its best, either all in one step or subsequent steps or whatever. It tries to drop back down closer to the nucleus where it was originally. Now, when it drops back down, guess what happens? It has to release energy. It cannot take that energy that it has and move closer than where it is. The only way it can move closer is to release some energy. So when that electron drops down to try to release some energy, or try to get closer to the nucleus, it ends up releasing energy. Okay? And we witness that. In this particular case, if this would have, take a look at this. When it dropped all the way out, and then it fell all the way back down. If this would have started here, went all the way up to here, fell all the way back down, the same energy that was absorbed would have been released. Like if it was blue light, and it was pure blue light that was being shot into this, it would have got absorbed, kicked out. When it fell back down, it would have got emitted again. Whatever came in would be the same as what came out. However, generally, that doesn't happen all the time. Some of it got released. So instead of falling all the way back down, if that electron only falls down one level, this energy change to go from, we'll say n equals, this is n equals 3, we'll say, this line right here, okay? To go from 3 to 2, that's a lot shorter fall than to go from 3 to 1, which is what this would have been, right? So the bigger the fall, the bigger the energy gap between them. So if this one's only fallen from n equals 3 to n equals 2, the energy associated with that release is going to be less than the energy that came in, right? Because not all of the energy was given off. Some of it's still inside that electron because it didn't fall down all the way. It's out here a little bit farther. So in this case, what you can see is a wavelength that comes in that's given off as a longer wavelength. Does that make sense? Think about it. I've got an electron that absorbs a certain wavelength of energy, a short wavelength, high energy. Okay? It gets kicked up. Immediately when it gets kicked up, it falls back down. We just showed it on the other side now. And if it doesn't fall all the way back down, it doesn't release all of that energy. So if it doesn't release all of that energy, the wavelength associated with it is going to be longer than what you started with. Okay? So like in this case, you could absorb blue light and give off red light, something like that. So what we usually see here is some sort of energy absorption is probably not going to be light. Say it's UV light. UV light is very energetic. It's very small. Some of these the electron in hydrogen, for example, could absorb some of that, and when it absorbs it and it starts to fall back down, it could release some of that energy. But it's probably not going to release all of that energy, but it could release some that fall within the visible spectrum. And if that wavelength that's emitted falls within the visible spectrum, that collection of atoms glows, and it gives off light. And that's whatever wavelength that is, whatever photons, wavelength associated with these photons or packets of energy that are given off as the color that we see. Okay? All right. Now, the most stable form of hydrogen is what's called its ground state in terms of where its electron is, and it would be that one, that first circle. Okay, that first electron that's buzzing, the only electron that's buzzing around that first level in the Bohr atom, we call it its ground state, and it says it's the lowest amount of energy. What you'll see is that's what an atom tries to do, is to reach its ground state, to reach a level, a positioning of its electrons as to minimize all of its energy. Okay. Now, in that case, if we get into the first orbital, or the first orbit there for that electron, that's ground state for hydrogen. That's the lowest energy that it can possess. Okay? Now, anytime it gains energy, the electron leaps up to a higher energy orbit. That's an example of an excited state for that hydrogen atom. So there's one ground state. There could be multiple excited states that go along with this. It's obviously it's much less stable in an excited state. So the second that it gains that energy, it wants to release it again, either all of it or part of it. It'll do something to try in an attempt to get back to the ground state. Okay. What's nice about hydrogen, it's very simple. It's very small. And what is true about all atoms that are the same, like whether it's nickel atoms, a bunch of nickel atoms, a bunch of hydrogens, whatever, as long as you have a group that are the same, we know that they have identical orbits. Their electrons, there has to be the same number, they're the same type of atom, and all that kind of stuff. So in this case, every hydrogen atom can undergo the same energy transitions. Okay. In the case of hydrogen, we saw that there were 4 lines on the emission spectrum. There are actually 4 different situations, we'll say, that these excited states can exist in. It can go from a high level to down to here, maybe farther, maybe in between, but there are generally all hydrogen atoms undergo the same types of where they absorb and where they fall to. Okay, that's what makes them hydrogen atoms. It's part of their chemical properties. Now, what we cannot assume is always the case is it says here the distances between the orbits in an atom are not all the same. No 2 leaps in an atom will have the same energy, because you cannot guarantee that when you have this hydrogen atom and this hydrogen atom, and you give energy to both of them, what you cannot assume is that if you have the electron in n equals 1 here, it's going to go up to 5 and down to 4, because over here it might go up to 4 and down to 2. You see what I mean? It's independent for each hydrogen. But the possibilities are the same for both of them. There's only the same number of places that they can go in each one, but for any given hydrogen at any given time, you don't know which one that atom is going to be employing at that instant. Okay? And if you have a large collection of hydrogen gas, think of all the things that are happening at the same time. Some of them are going 4 to 2, 3 to 1, whatever. But each one of them only have a certain set of 4 to choose from. We don't know which one's doing what at any given time. Okay, the closer the orbits are in energy, I showed you, like n equals 2, n equals 3. The closer they are, the lower the energy of the photon is going to be emitted when that electron drops. It's less energy to fall. The bigger the fall, if you go from like 5 all the way closer down to 1 to the nucleus, that's going to be a much bigger energy release. That means it's going to be a shorter wavelength, okay, in terms of visible light. So what you get is whenever you take a sample of hydrogen atoms and you excite them, what is reflected on the emission spectrum are all the possibilities that are happening with all the hydrogens present in your sample. Okay? You see some of them that are giving off this particular wavelength, some of them that are giving off this particular wavelength, and probably bouncing around at any given time. Because the second that it absorbs energy, it releases energy, then it's reloaded, it can do it again, just over and over, back and forth, with billions and billions and trillions and gazillions of hydrogen atoms. The other ones have multiple electrons. So how do you explain what goes on, how do you explain the emission spectrum when you start getting electrons that are all working against each other, working with each other, all happening at the same time, and instead of just having one electron to keep track of, you've got maybe even 100 or over 100, giving some atoms. In which case, it's not just statistical probability here. You can't just come up with all the possible combinations because they've tried that and it doesn't work. It doesn't explain the emission spectrum that we see. So I know this doesn't mean much to you, but what happened is they ran these emission spectra on these big elements after hydrogen, even a couple elements after hydrogen, even into lithium and boron and that kind of stuff, 4 or 5 electrons kind of thing. And especially when you get into transition metals, okay, that D block in the middle of the periodic table with iron and copper and all that, that's really screwy. Because what they started to see was the way that Bohr explained it doesn't work. It doesn't explain what we are seeing with all of these other types of atoms that are out there. It works very well for hydrogen. And if he wouldn't have figured that out, then they couldn't have figured out the next step. Okay? But it's really cool. So it does not, all the math that he used fails when it comes to atoms that have more than one electron. Okay? It does not account for, and this is what's Twilight Zone-y and kind of freaky shoutish, is it cannot account for electron-electron interactions. When electrons are present, and there's more than one, they can interact with each other. And as they interact with each other, the possibilities are endless in terms of what controls what's going on here and how to predict what's going to occur and that kind of thing. All right. A better theory was needed, and you're going to see that it's called quantum mechanics. Okay, I'm going to come back to that animation here. Quantum mechanics is a fancy way of basically looking at the mechanics of an atom. Quantum means to measure, to assign a number to. We're going to take the mechanical workings of an atom, employ a little math, employ a little numbers, and that kind of stuff. I assure you, it's nowhere. We're not going to touch on anywhere of the math that need to be touched on in here. But it's interesting. This is another icon, Erwin Schrödinger. Everybody should know that guy, but you don't. Look at him. He's like male supermodel, Erwin Schrödinger. With the name of Erwin, I mean, I don't know. Okay, well, I'm going to, before I do that, I want to show you this. I really hope it's still here because it's really cool. Don't make fun of it. It takes about 5 minutes to watch this, so better than me up here talking. For both of us. Careful. I should have had this set up before I started, but I didn't have time. Here, wait a minute. I'm going to...
Quantum weirdness. The infamous double slit experiment.
Oh, we got to let this load here.
To understand this experiment, we first need to see
I'm going to let it load first, so we don't get interrupted in the beginning. In the meantime, I'll talk about the next slide. It's cool. You'll like it. It's cool. Huh? All right. Now, here's what you're going to find out, and this is what you're going to see from this. This video is going to discuss a very, very famous experiment that was conducted. It's called the double slit experiment. Double slit experiment, okay? And you'll see what it means and the implications of it on this animation. But up until this point, we were considering energy. We considered then that led into a discussion of electrons and how electrons are associated with energy. And if you think about a pool, like a wave pool, okay? Imagine you're at Holiday World, or whatever theme park of your personal preference that has a wave pool, and no one was in it, okay? And the wave started going. It was propagating a wave towards the end of the pool. And you had this giant contraption that was like a solid board that could stretch all the way across, okay? It could stretch all the way across the length of the pool and basically block the water from coming through. But instead, in the very middle, you had a slit about this big. So basically you had two boards, right, that didn't meet all the way in the middle. and you allowed that wave to come in, and you were watching it as an observer, especially like climb up on the lifeguard chair or something, and you're watching this, and you see that wave propagating as it comes towards this slit, and it passes through that slit, I want you to get an idea in your head as to what you think the wave will look like when it passes through that slit. How will it change? What will the water look like? When you drop a pebble in the water, rings come out, and rings just keep going, right? What if you're pushing water like that through a little hole, through that slit? What will it look like on the other side of that slit? Okay, that's going to be a wave phenomenon. Get an image in your head. We'll see if you're right when you watch this. Secondly, if you think about like a little gun, okay, like a little BB gun or something that shoots tiny little pellets, and do the same thing. Okay, put a now imagine. I guess I should backtrack before we do that. With this water thing, imagine that at the end of the pool, as if it was coming this way, if the wave was being pushed from this side, there was a slit right here in the middle, and there was some sort of film that was along that wall that could map as to when the wave hit it, the spots where the wave hit. You know what I mean? Now, at the same time, imagine you had the same slit. Instead of using water, you used like BBs or some kind of pellets, and you sat back here and you had an automatic rifle that shot these BBs. If I had that when I was a kid, that would have been way cool. But say you have this back here and you start spraying it, okay, and some of them come through this slit. Imagine what that's going to look like when it hits the wall, and it hits that film back there, and it keeps track of where these things land. How will that look different, or will it look different from that wave that passed through? Okay? Then imagine if I had two slits at the same time. And if I had two slits apart from each other, say one up here, one over there, and that wave was coming through, and that wave passed through those two slits, what would it look like back there? And if I did the same thing with my gun that I was shooting, and I shot it, sprayed it, and kept going back and forth and sprayed between these two slits right here, how would that look on the wall when those things landed towards the back? Now, the results might surprise you a little bit, as they did with the researchers who did this with electrons. They took electrons, and they shot it through these slits, and they saw something really weird. They saw a mixture between what the water waves would have done and what the actual matter would have done had it been shot through. Now, this blew people's minds, and you'll see why. Okay, it's a little bit scary. Let's see if it's loaded up now.
Of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter. Like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern.
I want you to understand. You make fun of it if you want. But I want you to understand the implications of what you just saw. When shot through one slit, electrons behave like matter. When shot through two slits, behaves like waves. Right? Why? How can you possibly explain this? That doesn't even make any logical sense. Well, let's see. It's a good question. Thanks for the lead-in.
We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave?
The drama. I love this drama.
It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge.
I got goosebumps. You got goosebumps?
Inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly.
That's not the actual device.
But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of any.
Now, do you understand what just happened? Okay, wait a minute. You've got passing through a single slit, the electrons behaved like matter. They would follow like you were shooting something through there. Pass through two slits, interference pattern. The bands that you see on the back of that wall were like a wave that would have passed through. So they thought, as someone else brought up, what could be causing this interference pattern? Are they bouncing off each other? So they eliminated that possibility by shooting electrons through one at a time. By shooting through one at a time, they were not able to bounce off each other, right? Still, we had an interference pattern. How? So they're saying, okay, the only possibility is that these electrons come up to this gate, come up to these slits, turn into energy, turn into a wave, pass through, and then reunite on the other side, and that's what it causes all this interference pattern. So they're saying they split into energy before that happens, so that matter, energy, they convert between matter and energy all at once. And that's freaky if you think about it. Now, is that true? Well, the only way they would know is if they could set up a device, obviously not that simple, but if they could set up a device to actually watch this electron the moment it comes in contact with this slit. Which one does it go into? Does it split? Does it go into one? Does it go into the other? Does it go into neither? How do you do this? Well, here's what they found. Every single time you try to watch an electron, it's matter. If you're not watching it and you only see the result,
Only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
this is actually that last scene that you saw there. Yeah, it was. She's in that movie. There's a movie called it's, What the Bleep, something. It's if you've never seen it, it's at least the first part when they're discussing quantum mechanics. It's very interesting. The neural anatomy part and the whole brain stuff at the end is a little more boring, but it's still neat. But anyways, what does this have to do with anything we're talking about? I want you to understand that there's something called, well, when you're dealing with an electron, it borders on our definition in terms of what is matter and what is energy. Realize that electrons are the basis of all chemistry. All of these atoms that exist with their protons and electrons, I mean, you're right, all of this is very important, and everything that we learned about is very important. But what governs their interaction? What is the fundamental controlling force behind all of matter and all that we experience as reality? Are these electrons that are buzzing around these atoms and how they move and how they interact with one another. So then what gets thrown into question here is what reality actually is. If the fundamental basis of our reality is the movement of these electrons, and they form what we consider matter and all that is, if they can switch back and forth between matter and energy, then what is reality? What is matter actually, other than fixated energy that by observing we fixate ourselves? Like we see it, so we turn it into matter. When actually, from another observer, it could just be energy. Think about it. Okay? It's crazy. It's deep. But it's very interesting because what they're saying is the electron, we see the effects of electron when we just let it go. We see that sometimes it acts as matter, sometimes it acts as energy. But when we try to observe it, and we actually try to watch and predict and imagine and see up close what it is actually doing and try to figure out at the fundamental level how all this works, we see that it won't let us. We see that it becomes, at that point, it sticks to matter. Any possible energy that it could be, it uses the word superimpose. That means stick everything together. Take all the different energy forms that are there and collapse it. It says collapses it. Collapses it all into a unit of matter at that point. So if we were observing from anywhere else, it could be that you as an observer are making that electron involved with whatever atoms you are looking at. You are making that matter just by observing it. Okay? And you are limited to that. You will never know that it's anything else because if you try to look, you'll never find it. It'll always be matter according to your perception. And only when we can get outside of our minds and outside of this could you see the other possibilities. Okay? It's crazy stuff, folks. It's crazy stuff. Anyways, that being said, instead we're going to dive into what's called quantum events or quantum theory or quantum mechanics. When people found this stuff out, it obviously bothered them very much. Albert Einstein, right? We've all heard of Albert Einstein. Albert Einstein actually said, I wish I would have never have learned anything about this. That's what he said. If Einstein never wanted to learn it, it's got to say something for it. Okay? His exact quote was, I wish I had nothing to do with it, yada, 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 something else. And he said that God doesn't play dice with the universe. Because what this basically means is that all of this determinism, all of these things that we thought were so predictable, the planning of events, and what matter is, and what reality is, and how we shape our reality, is just a big figment of us creating matter based upon our observations. Okay? It basically means that these guys are all moving around at any given time. If you've got all this energy floating around with these electrons, that any other person could fixate them in a different way. Okay? We've just, with all the paradigms of thought that we have rolling around us, we've been so conditioned to train and to think in certain ways. Okay? Anyways, there's so much to say in terms of, so what about determinism? What about probability? We can't say for certain that things are going to happen. Can we predict events that are probable? What does this mean in terms of probability? Can we throw it all out the window? Should we just quit? Should we just throw it all in and say life's not worthwhile? I don't know. But now in the case of the quantum mechanical model, I want you to understand that what's different between this and the Bohr model is These are not orbits that these electrons are traveling in now. We're looking at a different type of atom, an atom that is able to use its electrons for many more things, okay, in terms of creating matter. So what we've got now is a level of organization with multi-electron atoms, things that have more than one electron. We've got a much more sophisticated organization than we ever thought was possible. Okay? They're not just a bunch of dots buzzing around a nucleus anymore. Their position and their behavior and their movement is of utmost importance to the fundamental basis of what we know as reality. Okay, so we say that in the quantum mechanical model, since there's no way, there's something called a Heisenberg uncertainty principle. It's one of the most important principles stated by a scientist, stated by Heisenberg, that has to do with chemistry and the physical sciences. He's saying there's no way that you can know where an electron is. There's no way. And the reason that there's no way is because just by looking at it, you've affected it. Just by trying to measure it, as this experiment showed, just by trying to measure it, you change the course of its action. So you'll never know where it actually is. You can look back on that film and see what's on the pack and get an idea of where it spends its most time, where it's going to land, and that kind of stuff. But you'll never know exactly where it's at. Not only that, but think back to the quantum leap thing, right? When it moves from one place to another in the atom, we don't even see where it goes. It disappears and it reappears. Okay, so there's no way that we can know all this kind of stuff. So what we can make is basically a map of an atom and plot where the probability will be of finding an electron at any given time. Okay? We can, not for certain, we can't draw little circles around it like Bohr did and say, here's 1, here's 2, here's 3, and here's where this electron's always going to be, and then there's going to be 2 here, and then there's going to be 3 more outside that, and so on and so forth. It doesn't quite work like that. But what we can do is get a probability map. Not the actual path that it follows, but the chances of finding it in a certain region at any given time. Okay? So we're going to change the word orbit to orbital. Orbital is not an orbit, like a planet, but it's a region. It's like a shell region in which you create a boundary in which you can find an electron at any given time. Okay? It may be like a sphere, like an invisible sphere, just like an arbitrary boundary that you've defined as a certain size of sphere that exists outside this electron, or outside this atom, and that electron can buzz around anywhere inside that sphere. Okay, that would be an orbital. Okay, now, as far as the math that went behind this, just appreciate it. Okay, I'm not going to show it to you. As far as the math that these physicists put into this to come up with this quantum theory model, years and years of the greatest minds of research still working on it. Okay, but generally it's set at about 90 or 95% confidence in terms of saying, you can say with about 90 to 95% confidence that you are right, that that's where an electron can be found at any given time. That there's no way to be absolutely correct. So, since we cannot describe their exact paths, and we don't know how and where electrons go at any given time, just where they're likely to show up, we cannot predict their behavior. So what about determinism? For those of us who believe that everything is determined. I'm not saying that it's not. I'm just saying from a scientific perspective, let's analyze this. If everything is determined, and the course of events is set into play that's going to play out a certain way because of the way that it's set up, and because of the interactions that will occur, what you got to realize is whatever is happening here, from an electron perspective, which governs all chemical reactions, which governs all of life and all of existence, down here, you cannot predict what these electrons are going to behave like, and thus you cannot predict the behavior of matter down the line, because you cannot predict the behavior of electrons. It can't happen. All right. It's interesting. All right, so put it in a baseball perspective. If you're dealing with a pitcher, okay, and to throw home, why'd I pick this, right? Why would I pick a baseball analogy? Why would I pick Mark McGwire even? I don't know. No, my question is would you know where to put your glove? You can predict a baseball's path, unless you get in a good knuckleball. That's a whole different story. But if you can predict a baseball's path, by and large, okay? If I was throwing you the ball, and, for those of you who can catch, if you put the glove up, you can predict where it's going to come, and you can predict when to squeeze, you can predict when to catch it, okay? Now, you follow that path, that's what I'm saying. I say here, not if you're catching an electron. An electron's like the ultimate knuckleball for those sports enthusiasts, okay? There's no way you know where it's going to go at any given time. What we can do, though, is instead of looking at this perspective and predicting the path, if it's here, we can assume that it's going to be here, assuming you can pick up the seams and know it's a fastball. Okay? It's not going to slide away or anything. But if you start here, you can predict that it's going to be here. You can predict that it's going to be here. Over on the other side, the best we can do with an electron is not look at its path, but look at where it lands. We can take this and make a map out of this. And if we were transposing, like throwing an electron as opposed to a baseball, you might see that 70% of with 70% probability versus 40% versus 20%, you can plot where you're likely to find these guys and where they're going to land. That does not mean, understand, that you can trace it back from where it started and how it got there. All you can do is come up with probabilities that give you a good idea of where you can find it at any given time. So that would be, basically, how that would translate is, if I told you to catch an electron, you would probably want to put the glove, where the highest density of where that electron lands and hope that it lands there. You're playing the odds. Otherwise, and wear a cup if you're a guy, because you don't know where it's going to actually go, right? So, all right. That's the difference. All right. So, again, we have these quantum numbers, though. You'll see sort of the same thing, n equals 1, n equals 2, 3, 4, like we had in the Bohr model. But things are a little bit different. Okay, we've still got this. We're actually going to have 3 different things we're going to put together to describe the location. What we're coming up here with is a map to explain where electrons are in these atoms. When we had the Bohr model, we could just say it's in n equals 1. There was an electron floating around there. Wrong. We've got a much more specific address now that we have to give in order to say where an electron is in an atom. And you'll see what I mean as this plays out. We're going to call these numbers that we use quantum numbers, the numbers that we're going to be using to numerically describe where these electrons are. Okay? The base unit is called the principal quantum number. This is similar to Bohr's 1, 2, 3, 4, 5 kind of thing. How close is it? How far away at any given time can it reach from the nucleus, this particular electron? If it only goes this far, we'll say it's n equals 1. We'll say quantum number 1. If it goes this far, we'll say 2. This far, 3, and so on and so forth. It can be anywhere inside that at any given time, but that's the maximum distance it would travel. Okay? All right. Now, then what we're going to do is define, sort of like an address, right? If I say, where are you at right now, you could give me a very specific address, or you could say, I'm on planet Earth. Some of you, I would disagree. But you could say that you're on planet Earth. And that's very ambiguous, very vague. You could say, I'm in the United States of America. Again, you've narrowed it down, but I got a long figuring to do to figure out where it is exactly that you are. Then you can narrow it down to a state. You can narrow it down to a county, a city. You get the point. Same thing with an electron. Okay? Just saying n equals 1, you've given me a boundary in which to work, but there's actually another boundary inside that boundary that we can define to help me pinpoint where I can find this particular electron. So these are called subshells. Okay? So you have this sort of bigger shell, this quantum number out here, the main energy level, and within those are called subshells. The way that we're going to distinguish these subshells is by their shape. Okay? You'll see that there are different shapes of these subshells, and if you realize where these come from, it comes from if you could freeze time and take a bunch of pictures of where electrons are, and then you step back and you look at it, those dark spots where the electrons are, when you plot them together, it's sort of like they make a picture where they are. And that's where these shapes are coming from. If they make a spherical shape, meaning like at any given time, they could be all over a certain given distance from the nucleus, and I step back and look at that, it looks like a sphere. Okay? I would call that a certain subshell. Some of them look like dumbbell shape, like figure 8. They tend to travel in like a figure 8 around the nucleus. We don't know why. It's just what we observe. Okay? That would be a different shape. Now it's kind of hard, but stay with me here. However, whatever principal quantum number you are in, for example, if you're in n equals 1, the very first distance from the nucleus, there will only be one subshell there. If you go to n equals 2, there will be 2 subshells, 2 different shapes within that. If you go to n equals 3, to the third main level, you will find 3 subshells in there. So that shouldn't be too hard to grasp. Now, these subshells, we're going to use letters to describe these specific subshells that are inside this main energy level. Okay? We're going to use these, S, P, D, and F. Don't worry, you'll get used to them. We're going to use S, P, D, and F. They all have different shapes. Okay? They're in this order. First you're going to see this, then you're going to see that, then that, then that. And I'll explain these. Each kind of sublevel, which is this guy's in here, each of these have a different shape. Some of them are real funky. This is so funky your book doesn't even show you a picture of it. Your book shows you a picture of what a D subshell would look like in a bunch of different shapes. I don't know, there's like 5 different shapes, I think. The P is in there, it's sort of dumbbell shaped, and the S is spherically shaped. Okay? All right, now the shape is going to represent the probability map. The shape represents, if I was taking snapshots of fractions of a second of where electrons were, and I developed that film and I looked back, I would see the dots, when all stuck together, sort of make a shape. They look like a dumbbell, or it looks like a big circle, or something like that. This is where these electrons are going to be. That's where this shape comes from. Okay, now, I'm going to show you a picture of this stuff in a second. Try to stay with me here. N equals 1. This is our first distance from the nucleus. So here's my nucleus. I've got this perimeter that I've defined. And what this means is whatever electrons are in this first level do not go outside of this region right here, what we call N equals 1. The question now is how many electrons can fit in there at any given time, and what is the shape, and that kind of thing. Okay, we'll get there. And N equals 1, there is only one subshell. It ends up being the size of the entire main energy level. It's called the S subshell. I'll show you in a second, but the S subshell is a sphere. It looks like a 3-dimensional sphere. So if I have a nucleus, and I have, imagine a sphere like another beach ball or something blown up around with this in the center of it. Inside that beach ball, inside that sphere, I can have electrons bouncing around. And that sphere extends, the boundary of that sphere extends all the way to the edge of the boundary of this first energy level. Okay? So the first energy level actually in itself is that sphere. Okay? All right. Now, if I move out one, realize I'm building on top of what I already have. If I have this and I have this sphere wrapped around it, I'm going to put another energy level on top of this one that's going to enclose everything that I just had. Okay? The ones inside don't disappear. I'm going to put on top of that something bigger that goes, let's say, out to here. This will be my second main energy level. What can I have within this boundary now? I'll move my hands out, my nucleus down here, my first main energy level that's a sphere. It's an S subshell. That's the shape of it. It's in here. I move out and I go bigger. I'm at N equals 2, the second main level. What that means is that anywhere between my hands, imagine a sphere, electrons can roam. That means they can actually cross down into the other ones that I just said. They just can't go past this one. There are some electrons that this is their boundary. They can't go any farther than this. There are some electrons down here that can't go any farther than that. We can keep getting bigger and bigger. Now here's what makes it more difficult is that I say S and P. S was the sphere, right? What you will find is when we get to the second level, and we're out here, and you've got electrons buzzing around in this area, okay? Yes, there is a sphere, a whole other sphere on top of what we just saw, but also within that sphere, imagine having a clear beach ball and then having like 3 dumbbells that were inflated, and you crossed them all in the center, so they all pointed in different directions, but they only reached as far as the beach ball. So when you stuck it inside, they touched the edge of the beach ball. Okay? That's what we're talking about. What you've got there is our first main energy level with the sphere, electrons in it, our second main energy level with the sphere, but also with 3 dumbbells crossing to the edges of that sphere on the inside. There are some electrons that will use the entire sphere. There are some electrons that will limit themselves just to those dumbbells that are inside that sphere. Does that make sense? If it doesn't, you're with many people in the world. Okay? I wish I could find some good animations with this, and I wish I could do a bunch of balloon art, but I can't. So you try to stay with me here. Just imagine this in your head. Don't try to memorize. Don't try to do this. If you cannot conceptually understand this, you're going to have a problem. Just imagine this. Imagine a nucleus. Imagine electrons buzzing around. Realize that electrons are not going to just keep buzzing around, getting bigger and bigger and bigger, and then shoot off into space. That's not what they do. They orbit like planets, right? We don't just fly off. We've got counterbalancing gravities all over the place that hold us and fixate us in certain positions. Electrons are the same way. You've got this nucleus. You've got a couple of electrons here that are buzzing around real close to that nucleus. there's a distance that they do not exceed. They do not go, these couple of electrons don't go past a certain point. We call that point the first main energy level. Okay? Now there are, in bigger atoms, there are more electrons. And some of those other electrons, besides, let's say, those first two, have the ability to swing out a little bit wider. They can take a bigger path. They don't escape. They can cut down in, they can cut across, they can do all kinds of things, but they're limited by this invisible sphere that's around them. They don't go past that. Does that make sense? All right, that's the second main energy level. Now, in the second main energy level, not only is that sphere present, but if you can imagine that some electrons, not only are they restricted by that sphere, but they are further restricted by additional shapes that confine them within that sphere. It's sort of like if I gave you this as the boundary of your room, but I started over here and I drew a figure 8 that went from that corner to that corner. Technically, your span, where you could take place in this room, you have one side to the other that you can have. You fill the entire size of this orbital, right? If you walk from this corner all the way to that corner, you've reached from one side of the boundary to the other. The difference is, what if I took some paint and I drew a figure 8 that went around, crossed in the middle, went around again, and met back in that corner? In that case, if you're an electron, that means you can buzz, but you can't go that way. You've got to stay within your figure 8, but you can go all the way to the end if you want. You're limited. Not only are you limited by the walls of this room, you're further limited by the shape of that figure 8 that's in that room. Does that make sense? Okay, that's the P versus the S. The S would be like this whole room. The P would be like another shape within that room that's further restricting some of those electrons. Okay? That's a P subshell. Well, we don't know because we can't watch individual electrons. But what we do know is, in terms of numbers, we only find a certain number in S at any given time and a certain number in P at any given time. But to keep track of individual electrons, there's no way of knowing that, based upon what we just saw with quantum theory. Okay, now, when you get to n equals 3, I want you to look in your book and see this picture and see how things get crazy now. Okay? Look at page 276. If you don't have a book, take a look at somebody's. Look at page 276. Well, first of all, look at page 275, and you'll see what I mean by S and P orbitals. S are those spheres, okay? Every energy level has an S orbital, right? It has a sphere that defines the boundary for every energy level. And then once P appears, okay, once the P orbital appears, it stays within those energy levels from that point on, right, as you go up. You'll see that it's sort of dumbbell-shaped, and it's pointed in the X, Y, and Z direction for 3 dimensions. It goes in all directions. Now, in addition to that, so you've got S, once you get to the second level, you've got S and P in there, okay? When you get to the third level, not only do you have S, and not only do you have P, you have D, and take a look at that shapes of D on page 276. All of those shapes are occurring within that sphere of quantum level 3. So if we're up here and we get to level 3, we've got a sphere, we've got dumbbell shapes within inside that sphere, and we've got all those shapes inside that sphere. Okay? Imagine the complexity here.
So we're at 3.
Okay?
We have a sphere around the first level.
Right?
Does that sphere get as big as the second level with the dumbbells in the middle, or is the sphere here the second sphere?
Okay, I don't think I followed you. Go again. Where are you starting right here? Is that 1, 2, or 3? Okay, you're at 1. Right.
And so then when we go up to 2, which is the P, does this sphere...
2 is still going to have an S, but it's going to add a P.
Right.
Okay.
So my question is, does S stay here?
That S does. That's 1 S.
Okay, then you get your second S.
That's right. It's a separate S.
And so theoretically you have 2 spheres and the dumbbell.
Yes. With one sphere being bigger than the other.
Bigger following the second.
Yes.
So when we get to 3, there's 3 spheres.
Yes. 2 P's,
2 P's.
one smaller than the other. Yeah.
And that, which is, D is virtually 2 P's, right?
No, D is something separate. D is all those happening at the same time.
So in D, on top of
D is with, what encloses everything? S, okay, listen. S encloses everything on every level.
So you always have a different size sphere for each.
Yes, yes, you have a different,
1, 2, 3, 4 spheres.
that's right.
In them are
All these other things. Yes, that's exactly right. That's exactly right. Okay? All right, now, F, listen, shh, F is even more complicated than D to the point where they didn't even include the illustrations. Okay? Now those are going on. F starts when you get to the 4th main energy level, away from the nucleus. So here's what I want you to imagine. Imagine the difference in terms of complexity of electron arrangement between a hydrogen atom and, say, a uranium atom or a plutonium atom. Think about how many electrons they have and how they must be distributed. When you have hydrogen, the only thing you need is this. You have one subshell. Because you only have one electron, obviously that one electron is going to fit inside that. That's it. One main energy level with that S shape to it. That's it. We call it 1s. Then you could go to 2s. And within that is 2p. Then you could go to 3s. You've got 3s, 3p, 3d. Right? You can go to 4s. 4s, 4p, 4d, 4f. All those fit inside that sphere. So the bigger your atom gets, the more electrons that you have, the more incredibly complex its electronic structure becomes. That helps us predict how these things are going to act. Okay? All right. Here's a sphere. Yep. Actually, okay, I'm getting there. I'll get there. But just keep this in mind. The more restrictive the shape is, the more energy it's going to give that electron. The more restrictive it is. P is more restrictive than S. It confines you more. D does even more confining. F even confines it more. The more confining that you do, the more energy those electrons are going to have. They're going to want to bust loose, basically. Yes. Okay, definitely. Yeah. Versus 4S, yes. Not versus 5S. 5s is farther away. I'm going to get there. Okay. Where this sort of sphere comes from is, like I said, probability maps. You plot those electrons, see where they land, and that's why we call it a sphere. They tend to stay within that area. Now, what I want you to understand is with a p orbital is actually, by definition, all three of these dumbbells together. It's not just one of them. Okay, so it consists of this, and this, what you see up here. All three of those dumbbells together within that sphere, that's the P sublevel. Okay? Uh-huh. Could. There's no way of us knowing. But it could. Because the second we tried to watch it, we would affect its behavior, so there's no way. What we can only do is look at the probability and see where things land. Could it be possible that it's switching from P to the, this P line here to the other one? Sure. Could it be possible that it's switching from P to another S somewhere else? It's possible, but there's no way of us watching that happen. All that we can do is look at the after effect and see where these things tend to land and predict it. We know probability and likelihood, but we never know for certain where it actually went and where it goes. Okay? There's D. Okay, a lot of stuff happening all at the same time in all different directions. This one's even funnier. It's got a little ring around the center. Don't ask me how to explain that. I have no idea. I just know that they're there. Right here, all we're doing is electrons. Sure, they study protons and neutrons. Take Chem 2. I'll tell you all about nuclear chemistry and the degradation and all that kind of stuff. Let's just keep it with electrons for right now. Let's just stick it with this. Don't look at P's. We're not looking at P's here. This is just D's. Okay, this is just D is all of this together at the same time. That summed it up right there. Holy crap. That's right. All right. Now, you're not going to have to know all those. I expect you to know the shape of S and P. That's easy. Spheres and dumbbells, that kind of thing. That's not hard. I will never ask you to draw all the possible combinations of the d orbital. It doesn't teach anyone anything. Okay, now, someone asked me about relative energies, because you're right. Okay, electrons, depending upon where they are located, how do we know they have different energies is because emission spectrums. We know that each one emits a little different wavelength of light. So how do we explain all this? That means electrons, based upon their position, must have different energies associated with them. So how do we determine now which ones are more energetic than the others? And where has research led us to? It is here. The subshells of a principal shell have slightly different energies. In other words, if I'm in level 3 and I have S, P, and D, the ones that are in S, the ones that are in P, and the ones that are in D have slightly different energies relative to one another. I said a second ago, the more restrictive the pattern is, the more energetic the electrons are going to be in. It's just like you. If someone puts you in a straitjacket, you're going to want to fidget to get out of it. You ain't going to be comfortable. Okay? Same thing with electrons. The tighter their space, the more energy they're going to have. The more they're going to bump into each other, and the more they're going to want to try to bust free, if you think about it that way, even though they won't. So what we're saying is, if you're in one level, if you're in, let's say, the 4th energy level, way out here, where you have S, P, D, and F all present, anything that's in F, because it has all those different shapes, it's more restrictive, is going to have the most energy than compared to electrons that are in the D. And the D are going to have more than the P, and the P are going to have more than the S. That's within the same main energy level. Okay? If we're like in 4, or if we're in 3, and you just have S, P, and D, D is going to have more energy than P, which is going to have more energy than S. Okay? If you're down to 2, you're just going to have P and S. P is going to have more energy than S. However, realize that the main energy, anything in a main energy level, like if I have 1, right, and I have 1s, and then I go to 2s, anything that's in the 2nd level, no matter what the shape is going to have more energy than anything in the 1st level, because it's farther away from the nucleus. Okay? Remember, the farther away we go, the more energy it has. So anything in 1 is going to be less than anything in 2, but anything in 2, you have to look at S and P. Okay? Within 2, how do 2 electrons compare? Well, whichever one's S is going to have lower energy than the one that's in P. Okay, now, the S subshell, I say, has 1 orbital. In other words, 1 place to stick electrons. It's a sphere. You can stick electrons anywhere in that sphere, right? That's easy enough. When I say the P subshells have 3 orbitals, that means the dumbbell, I said there was 3 of them, right? There's 1 on each axis for 3 dimensions. So each 3 of those orbitals make up the entire P subshell. Okay? When you look at D, you can count them. There are 5 orbitals all at the same time. That all makes the D subshell. If you would look at F, there are actually 7. Okay? There's 7 different orbitals that make up that F subshell. That's within that whatever energy level you would happen to be in at that time. At least 4. Okay. Now, just like what Bohr said with his hydrogen model, when these things move between these regions that we're talking about, energy changes happen. If you go from somewhere like a 3p to a 3s, you're going to get an energy release. You've got a loss in energy. It has to go somewhere. If you go from a 3s to a 3p, assuming you can do that, or from a 3s to a 4s, anytime you go up in energy, there has to be an energy input into that atom to make it occur. Okay? Not from a 3, oh yeah, 3p to a 3s, you're right. There will be a small release of energy. That's right, because p has more energy than what s would have. You're right, it would be smaller, but it would be a release of energy. Now, the ground state of this electron now becomes a little more complicated than Bohr's model, where we just said, the electron's in the 1st orbital, we're good to go. The ground state here is the lowest, whatever configuration you can use, using all your orbitals. How can you pack these electrons in to create the situation with the least amount of energy? If you can do that, you've got the ground state of that atom. That's a little bit bigger of a task than the previous model that we used, but it's possible. All right. Higher energy orbitals then, just like before, are considered excited states. It's just we've got a lot more detail now. Only the quantum mechanical model, which is what we're dealing with here. Okay? The quantum mechanics is basically the math behind how the atom works. Only this model can predict the spectra of all the other atoms that we see, that we measure. Now, I want to go a little bit into this before I let you go so you have some stuff to work on with the problems. Now, there is a way. Obviously, if I wanted to ask you and I said, I want you to take a boron atom and draw me all the subshells that are there. How many electrons does it have, and all the possible arrangements based upon what you know S is shaped like and P shaped like and all that kind of stuff. You could do it, right? It would be just a tedious task to actually try to, especially if you're not very good at drawing and get it in 3 dimensions and that kind of thing. That's why, since chemists are not artists, it's best to use numbers and letters whenever possible, as opposed to draw pictures. So that's what we're going to do. We're going to be able to say, for example, if I say 1s2, that is what's called the electron configuration for, that's actually wrong. That would have to, hydrogen only has 1 electron, right? So that would have to be helium. You might want to make that change, okay? So you don't get confused. I just caught that. I don't know how I didn't catch that last semester. If this was He and was helium, and I say that it's 1s2, what do you think that means? Just guess. Somebody tell me what 1s2 probably means. It's got 2 electrons where? In the first main energy level, which is nothing but a sphere, right? That's why we call it S. So we say 1s2, there's 2 electrons in that. That's where they are. There's only 2 electrons in helium, and they're both in the first main energy level in that shape of a sphere, which we call S. Okay? Now, here's what you need to know. Every orbital that we looked at, when I say orbital, I mean the P has 3 orbitals, the D has 5 orbitals, right? The F has 7 orbitals. Every single one of those separate pictures that make an orbital, there's 3 of them, you put them together to get a P. Every single one of those dumbbells, for example, in P, can hold 2 electrons. Every picture that you see, every orbital that we've talked about will hold 2 electrons. So that 1s will hold 2 electrons. What if I jump out to 2s? How many will 2s hold? Let's limit it just to the 2s. 2. There'll be 4 if you count what's underneath it. I'm not counting that. Just count the 2s. There's 2 more in the 2s. What about 2p? 6, right? You're right with 2, but each orbital has 2, right? So since there's 3 orbitals, it'll hold actually 6 electrons in that p subshell altogether. Think about D. It has 5 orbitals. How many electrons can be housed in the D subshell? 10. Since F has 7, it can hold 14. That's where these numbers come from. Okay? All right. That's how many electrons each one can hold. So basically, all you've got to do is figure out the order. If you go from 1s, where do you go next? Then what happens? Then where do you go? Then where do you go? And when you can figure out your order and you know how many with each P and with each S that you can put in there, you can start writing configurations and you can start telling someone else, like me most importantly, where these electrons are located in an atom. Okay, now hang on one sec. I want you to understand that we're going to take these electrons, we're going to place them starting at the bottom. If you were building an atom, you would put them in the lowest energy position first and then build up from there. We call this the Aufbau principle. Everybody speaks German. Aufbauen is to build up, right? So from the lower energy all the way up. So this is the last thing I'll say. Hang on. Notice that 1s is the lowest energy that we have. All right? We go up to a next level, we've got 2s. Now within that same energy level, we've got 2p, but I put them up a little higher because they're actually got a little bit more energy than what 2s have, right? So this would fill up first. You'd have 2 electrons here. You could have 2 electrons here, 2 here, 2 here, 2 here. That's 2, 4, 6, 8, 10. That means for the first 10 elements on the periodic table, this is all you would need to write their configurations up to the 2p level, right? Because atomic number 10, if it's charged neutral, that means it has 10 protons and thus 10 electrons. Okay? All right. Next is 3s. Next is 3p. And this is where I want to end. I want to point out to you. This is where it gets screwy. Okay? This is where the transition metals start, by the way, and I'll point that out. Actually, when you have 3p, you will fill the 4s shell before you fill the 3d shell. I'll leave the explanation this maybe another time, perhaps even another class. But I'll explain. I'll explain. I'll explain that later. For this class, yep, they were trying to oversimplify. Like for biology classes and stuff.
The first orbital has 2, and then the maximum of each one after that is at 8.
Sort of. I'm going to explain that.
But you just throw that out the window.
Because I'm not to the maximum outside. You will see that when we get to the very, very